The atomic model for hydrogen. When you picture an atom according to the Bohr-Rutherford atomic model, there is a nucleus and there are electron shells around it. For hydrogen, the atomic model looks something like this. The nucleus is the charge-dense region located in the center. And the electron shells that we can symbolize with a larger circle around it, around the nucleus, they are always there. However, they may not all be filled with electrons. So for hydrogen, we have one electron in the first and its outermost shell. So we have here an electron located on its first and, of course, outermost shell. The proton that we already mentioned in the case of hydrogen in the previous video is located in the nucleus or is in fact the nucleus. So we've got a positively charged proton right here in the center, and the electron just orbits around the nucleus, around the positively charged proton. So we can symbolize the electron with a small case letter, a lowercase letter e. And even though the electron and the proton here seem to have similar sizes, the electron only has a mass which is 1 to 1836 of that of a proton. So the electron is really, really small compared to the proton. And the proton is 1836 times bigger than the electron. So this ratio is like if you compare the size of a diver and who swims around a large blue whale, for example. Electrons are subatomic particles. Electrons are subatomic particles. And that means that they are the building blocks of atoms, just like the protons, of course. However, the electron does not consist of any known smaller particles, like protons consist of quarks. Electrons are what we call, and have already mentioned before, they are elementary particles. Elementary particles. And electrons carry one elementary charge of minus 1e. Protons also carry a charge of the exact opposite to the charge of an electron, which is plus 1e. In the case of hydrogen, we need one electron with a negative charge of -1 here in its first outer shell to balance the one positive charge in the atom nucleus. At least this is the way elements are represented in the periodic table of elements. They are represented neutral to the outside. In the previous video, we said that sometimes we refer to hydrogen as proton. Hydrogen and proton are used interchangeably. When would that happen? That happens, for example, when an acid is dissolved in water. It increases the concentration of H+ ions or protons. So, if a molecule behaves like that in water, it can be considered to be a proton donor or an H+ donor. It gives a proton, that's what that means. And then it can be called an Arrhenius acid, because Arrhenius was the scientist who developed this idea. So, for example, if we take hydrochloric acid, HCl, and we dissolve it in water, we have a reaction here that first of all dissociates the hydrochloric acid into chlorine, which is negatively charged, and into one proton. That is what we see up here. If we simply remove this electron, we are only left with one proton. And this is the reason why hydrogen and proton can be used in some cases interchangeably, because now that the chemical bond between the chlorine and the hydrogen is broken, we are only left with an H+ in theory. However, the H+ or the proton is unstable alone. And that is the reason why it usually forms a hydronium ion in connection with water. So the H+ becomes part of the water molecule. We simply add this H to this water, which gives us 3H here. So here, in theory, we have H1, but nobody writes H1. As soon as we don't have an indication what number it is, we assume automatically it's 1. So let's remove the 1 here. And this way, we produce the protons from an acid that dissociates in water, and the proton connects to the water. And the reason why hydrochloric acid behaves like that is something we will discuss in our next section when we start to approach the periodic table of elements and the electron configurations. For the moment, let us take a step back and go over some new words we saw today, such as molecule, or hydronium ion, or electron. And let us define a little bit more precisely what they actually mean. A molecule is a group of two or more atoms held together by a chemical bond. And a chemical bond is simply a shared electron pair. But we will not focus on this now, because that will be again part of the discussion about electron configurations in the following video. But we bear this in mind, that atoms are held together in chemical bonds through a shared electron pair to form molecules. Molecules are groups of atoms held together by a chemical bond, and that chemical bond can be an electron pair. Or it can be through electrostatic forces in the case of salts, but this is also something that we will consider later on in more detail when we speak about electronegativity and electron configurations. For the moment, this is a good enough definition, and the term molecule is derived from a Latin word which means small unit of mass. Small unit of mass. Because molecules do not consist of any group of atoms, but of a particular ratio of groups of atoms. For example, HCl. There is one hydrogen atom and one chlorine. So there is a 1-to-1 ratio here. And then there are molecules that have a 2-to-1 ratio, like water. We have 2 hydrogen and 1 oxygen. And molecule means that groups of atoms with a particular ratio form a chemical bond. And all that meaning is contained in the small word molecule. We also mentioned hydronium ion. Let's first look at the word ion. Ion comes from Greek, again, a term from Greek, and means going. Because ions move, they are going towards the electrode of opposite charge. An ion is basically on the move. It's running somewhere, like a car. So that is what ion means. It's going somewhere to an opposite charge. Opposite charge. Hydronium consists of hydro and onium. Hydro or hydro and onium. In which hydro or hydro, this part, means water, and onium stands for addition of a proton. Addition of a proton. We're adding a proton, this one, to water to form the hydronium ion. And there are other onium ions, such as, and let's create some space here on the next slide. Such as ammonium. NH4 plus, because there is a proton attached to ammonia. NH3. And ammonia is used as a fertilizer for global food production, which is something that we're going to come back to in our considerations and applications for the use of hydrogen a little bit later. But this is just to show that the suffix onium is also used in other molecules, not only for the hydronium, but also for quite a common molecule, ammonium. And then we saw the electron. Electron comes from the Greek word for amber. Amber. Because the ancient Greeks noticed that after they rubbed fur on amber, the amber started to attract small objects, and it exerted this invisible force. Amber, by the way, is a type of yellow-brownish tree resin. It's a tree resin. And from this observation, the word electron comes. And it's actually quite a beautiful resin that can be found in nature. So we've made some good progress so far to define a few basic concepts on which we can continue to build our understanding for more complex relationships in chemistry. So let's continue with the periodic table of elements and electron configurations in the next video.